Okay, so welcome everyone to this new episode of Eaglefly, the experimental debugger. And uh, it's been a great day today. Um, Mainly because, well, it's good. It's good to be on Tuesday, and I love Tuesdays. Why not? So yeah, and I think we should start coding. So I think I'll be opening for coder for today. As I remember, where we left off on the last stream was that we were implementing loop-like code editing. For what we've done basically, and we were trying to understand a little bit more about um, how does virtual location proceeds, looking out through memory, how does processes manages, how the NT virtual memory manager handles all memory. I mean, handles memory to all the processes that are running actually. And yeah, I mean, we found something cool and interesting. I mean, how the processes work and all that stuff. And I think we should dig a little bit more into there because there's a whole. I mean, that's the bread and butter for this kind of how can I say? That's the some kind of essential thing that we have to understand and probably yeah. So let me see if I compile. Yes, it does. All right. So let me open msdef. And I would say that I would like to open the project and I would like to start, and there you go. So we have the live code editing, which is the thing to say that we want some kind of transformation on the code, and it happens, which is nice. And also I like to see what probably the implementation of loop-like code editing could do. In this case, I believe we set some usage code tests left here, if I do remember. Yeah, so we started to implement this. We have set some control key command that we can use. I believe it's control L. Yeah, yep. And if we do press that, we could start to begin the loop, and if we toggle it back, we could end the loop also. Or I mean, probably if I now that I think about it, I can say something like start recording. Start recording. It's better called start recording, I guess. And this is end recording, something like that. Probably this can be better. Probably want to do something like this. So yes, something like this. And probably, well, if we compile, we'll see our folder. Um, so yeah, probably want to have here something like it can be probably in the Win32 state, I guess. Well, So let me see. Let's go back onto the place where we left. The return address from the function is the virtual address of the first pages of committed addresses. Say for example you have a range of addresses where several subsets of the addresses are committed and others are reserved. So yeah, I can even draw this, so I can explain it. Do, do, do. I always forget. Yep. Man, what's going on? What's going on? So let's see. What I was trying to do or to explain is that let me move myself. Okay, so we have. Oh, oh, we're still moving. Awesome. So what's going on the last time that I was moving this thing? I mean, I'm moving, but the cursor changes, so that's weird. And if there you go. Okay, so I clicked space and now I'm writing, but I click space back and I'm not writing. And I'm not moving, sorry. What's going on, Milton? What's going on? Oh, I know. So probably you mean like this? No. Well, it doesn't matter. Okay, my good fellas. What I was trying to say is that we have a process. You know, this is a process. And this process is gonna have, you know, the memory, you know, 2 gigs. Oh my god. It's gonna have 2 gigs of available virtual address space, you know, and throughout the process, it's gonna, I mean, it's gonna be mapped. The virtual is gonna be randomized, you know. I mean, we don't know. I mean, we're assuming this is the process. This is the app process, you know. This is the app process. All right. And it's gonna have, you know, some are gonna be reserved. You know, it's gonna have a boundary. You know, this is not touched at all. And the same here. So this boundary is not touched. Oh my god. There you go. And for this space, we're gonna have a range of pages that they're gonna be, some of them they will be committed, some of them they will be free, some of them can be reserved. You know what I mean? So probably this is free, this is committed, this is reserved, and voila. You can commit it. Yeah. So we don't know. I mean, this is totally randomized, and the process and the mapper. We don't have control on how does this thing happens, because it's gonna be dynamically loaded. Even, I mean, it's gonna be, you know, probably, I mean, right here you have also the stack and the heap and everything, you know. But so my point was that if we're trying to debug this stuff, you know, if we're trying to debug this stuff, we probably want, we don't want to be here. I mean, we want the minimum thing happening throughout this. We don't want to interfere with the code, because I mean, this is totally bananas, you know. I mean, we don't know what's going on here, and probably, I mean, we want to make ourselves our life easier, because, you know, I mean, we don't want to mess with something. We don't want to mess with the process. So the thing that I was looking at and I was thinking through is that we should have our process. You know, this is the debug process, and we want some kind of systematic procedure, some kind of communication. You know what I mean? So these 2 processes have to have to communicate each other. I mean, the debugger is gonna call to the process, and we wanna say like, hey, give me the data, give me all your data, man. Well, give me the data that we want. and the process is gonna tell you, whoa, man, whoa, what are you looking for? Give me your data. And we want to have some systematic way of communication between the the app process and the debug process. And yeah, I mean, first of all, in the sense of a space, we want to have ourselves our own boundary here. You know, we want to say, I mean, we want to have our playground. We don't want to like, yeah, I mean, we want to have the minimum of necessary code to be managing whatever this thing has to send back to the debug process. You know, so if, for example, if we inject a DLL here, you know, like, you know, something like here is our DLL. This DLL has to have the possibility and the responsibility to, one, to control whatever the control for. I mean, this is gonna be like our manager, you know. This, I mean, even it can be like a manager, DLL manager or something. You want a manager that tells us uh, that acts like an arbitrary, you know, like it acts like an it controls what goes into what it doesn't, you know. I mean, probably this send a message, probably probably the debug process sends a message. You know, I mean, this whole thing, I mean, I'm just this is, I mean, this is life, man. I'm just inventing this so that I can reason about how we want this process, I mean, along understanding how the processes work and all this stuff. I like to do this kind of conscious reasoning about what's the best manner to allow the processes uh, to be efficient and to be independent, in the sense that the debug process doesn't have to care about the app process at all. The debug process should be just receiving the stuff, receive data, mirror data. It can be packets, it can be anything. And the DLL manager, that is this one guy, should be responsible for sending those packages of data out to this debug process somehow. And yeah, so this is the manager. This manager shouldn't mm-hmm, probably, I mean, since this how can I say, I mean, there are gonna be two quirky things here. One is a good one, and one is the how can I say, one is difficult and one is the simple one. For example, we can try. I mean, we know that function calls are just stacked on, you know, and I mean, we can skip right now multi-core thing and multi-processing thing, you know, just for being simple. We're gonna look at the stack, and the stack is simple in the sense that it's kind of deterministic on the way that it functions and the way it handles memory, you know, because the stack is really simple. It goes one way and then it goes back one way, so it's gonna grow this way and then it's gonna go back this way. That's what we assume. We don't know how much of it is gonna have, but I mean, we are still we at least know that we have this this kind of systematic procedure that memory goes in and out. So yeah, that's the easy part. The hard part is gonna be the virtual allocation processes, that, I mean, all this stuff, you know, all this stuff, all these things. I mean, we don't know. I mean, we don't know where they are. We don't know how does the process. I mean, the only place that we can know about it is that if we can, how can I say? if there's some kind of a way to access it. But probably we don't have to care right now much about it. We probably later want to handle that, because that's a more randomized thing that probably we don't have a complete sense of how this entity manager handles the process of allocation, you know. So, but we can start by this, and probably, I mean, this is a stack, and the stack is not even for I mean, we're talking here about variables, you know, variables. And there's also another part that's the code segment, and the code segment should be, well, I made some crazy mess here, but probably I can do this. And the code segment, Jesus Christ. Yeah, the code segment is gonna be this guy. This is the code segment, and the code segment, it's a static, you know. I mean, you cannot add something to the code segment, at least, at least, at least I think you cannot. So the code segment is gonna be static, and it's something also, something that we can start by there, you know, probably, in the sense of what's going on. I mean, this in relationship with the, how can I say, let me go back to this color, the code segment. Oh man. Oh man, the code segment is the code segment along with the stack is going to tell us basically uh, the the most important part of the processes, you know, along which the debugger can, which from we can handle all that data. But yeah, we have to dig a little bit more on how does for example, the dealer manager has to control these. Probably this is gonna have some requests, you know, some requests, and the dealer manager has to handle all those requests and sending packages back onto the debug process, you know. So for them to be some kind of collation here, or some way, you know. So yeah, so it's gonna be some some structure there, you know. But yeah, so let's go back here. That was just like a little conscious reasonance, how a way to, probably a way that we could do it, you know. It's not totally complete, I know, but that's the way it is. We have to start somewhere. All right, so let's continue with this. Yeah, we know that we have href, and let's see, this is important to remember when you need to commit a large range of addresses. Say for example, you have a range of addresses where several subsets of the addresses are committed and others are reserved. The only way to make the entire range reserved is to independently decommit each subset of the committed and one by one. Attempting to decommit the entire range of addresses will fail because reserved addresses cannot be decommitted. Conversely, the same range of addresses can be freed in one fell swoop. What the hell with that sample? The maximum number of pages that can be locked into a process working set at one time is limited to 32. An application could do more harm than good by locking pages that are committed into the working set, because doing so may force other critical pages in the process to become replaced. virtual address descriptor. And perceives by describing the memory ranges allocated by a process state might be seen by the process. Okay. As map files, loaded DLLs, or privately allocated regions. When a process allocates memory with virtual alloc, the memory manager creates an entry in the VAT tree. The tree itself is a self-balancing binary tree. At any given node, memory addresses lower than those contained. Memory addresses lower than those contained at the current node can be found in the left subtree and higher ranges in the right. Okay, I got you. There are three distinct types of VID node found in Windows 2000 and XP. The structures and these structures are named MMVAD short, MMVAD, and MMVAD long, and their format can be determined using. Okay, cool. MMVAD short, MMVAD, and MMVAD long. So probably it's just about how long, it's just the type of the memory address. Okay, sounds reasonable. Walking the tree is simply a matter of identifying the e-process structure for the process of interest. Locating the VAT root member offset 0 times 194 in Windows 3 or 0x11c in all versions, and then following each link to the left or right to trees until the entire tree is traversed. The reading is used for a map file, such as a loaded DLL. The corresponding file object structure can be Okay. It's something like VAD short with the address space, add an address space with a range, I guess. And then there's a short with some identifier with some to address space. Probably it's the range. A portion of the VAD tree for Notepad.exe. Alright. And then there's another VAD. This is the control area that it was. Notepad.exe. Okay. Okay. This is interesting. So basically, the Windows uses a self-balancing tree well, this is for Windows 2000 and XP. I don't know if it's still the same, but I can assume that it's a good starting point. So we have a self-balancing tree with the addresses of memory that gets allocated all the time, and this is just basically for virtual Alex and virtual freeze, I guess. So every time we add one, it goes and its order uh, from lowest to the biggest address space. So you have some blocks allocated. I mean, you can see like the timeline of processes allocation, because that's how it goes downward. If you go from top to down, you see the timeline of process allocation. Well, not necessarily, because it's self-balancing. If I assume, well, it depends on how it balances, but if it balances itself as a normal balanced tree, it will do some bananas there, and you wouldn't know which happened first or something. But at least you can know. I guess they do it because just for fast access and fast access and removal of the elements of the data structure, which is fine. And you need to have the page directory to traverse it. That's another important tool. You need the page directory. Given a process to blah 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 address space, managing the entire range of addresses will be difficult, because the addresses themselves are represented independent of the memory that may or may not be committed to them. Querying them is simply a matter of accessing the data structure that maintains their state. Okay, so this function basically traverses the VAD structure and exposes the capability of working with the virtual query and virtual query X functions again. So probably we can just, I mean, this is like a basic one, a basic way of trying to access it. It's like, oh, I want to see how the memories map in your address space. So if I'm another process, I can try to do it using virtual query X. Query next region of memory in child process. So you wish to determine how much stack space has been committed at any given time. Follow these steps. Get the thread context from the thread in question. Call the virtual query. Function. You cannot get a valid context from a running thread. Use the suspend thread function to suspend. right? Perfectly. So we can use suspend thread to basically have this breakpoint stuff functionality, which is nice. Okay, so that's important. We as users can only debug our processes. If we have another user, we have to use SE debug privilege. Okay, so we don't care too much about that, but it's good to know. Yeah, I mean, most of the time we want to just debug uh, processes that are run from the user only. So basically, this is the one that returns the handle to the thread, so we can create thread, open thread, or the other things, suspend thread, or Now I don't know, but I mean, they say something about how does the I mean, the probably the debugging process can be along a separate thread, you know, and this thread, uh, well, it makes sense, I guess. I mean, of course, it's not running on this same process as, I mean, if you're kind of debugging, you probably want to have that thread to be working alongside the other threads and processes. So it's more like if the DLL instantiates a thread module, well, a working thread to do all this kind of stuff. I mean, so basically, oh, so now I see. So the DLL will initialize a thread that can co-process along the system process, the application process, and in that manner, we can start to pull data out, uh, you know, somehow. Okay, okay, that's interesting. And yeah, it can probably work as a working thread or something. So, for example, one of the tasks of this thread should be to always get, uh, how can I say, yeah, to always get a valid, um, the current the current step of the process, you know, so as to uh, issue query for where the other processors are, you know, so it has to communicate with these other processes. Okay, 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 okay. Yeah, that explains a little bit more about how does this work. So we can start with the, I mean, to fetching and grabbing the current process state, because if we know that, well, we can start to implement the other functionalities, you know, like setting breakpoints or so all that basic functionality for the debugger, grabbing data values and everything else. It can come along that. I mean, just as watching how does that working thread works, uh, we can see what goes on. All right, sounds good for me. Okay, so many of the zero-time libraries are not thread safe. Okay, so that's all what you need to. I mean, a process is has a whole set of environment set for a program to execute. It has memory, well, not memory, but virtual address space, the code, the executable, open handles to system objects, which are all these handles to the system, a context, a unique process identifier, environment variables, a priority class that I guess is for the thread, minimum and maximum working set sizes, and at least one thread of execution. the scheduling priority, thread local storage, a unique thread identifier, in a set of structures the system we use to create to save the thread context until it is scheduled. The thread context includes the thread set of machine registers, the kernel stack, a thread environment block, and a user stack in the other space of the thread space. Okay. Okay, so it gives you the whole context of where the thread is executing, like the registers that he's using, the kernel stack, a thread environment block. The environment block. What's that? In a user stack in the other space. Okay, so there are two stacks. The user stack for in the address space of the process, and the kernel stack. So how? I mean, my question is. I mean, there are a number of threads processing, each with its own context. So each thread has its own. Yeah, it has its own stack. It owns. It moves now. Yeah. So you in within a process you schedule several threads, working threads. You will see that this stack will be like going on up and down for each of the thread independently. Right? So Microsoft Windows supports preemptive multitasking. Yeah. Which creates the effect of simultaneous execution of multiple threads from multiple processes. Okay, does that mean that it does? Or it's just, I mean, what does effect mean? On a multiprocessor computer, the system can simultaneously execute as many threads as there are processors on the computer. Yeah. Yeah, that's true. A job object allows groups of processes are nameable, secureable, shareable objects that control attributes of the processes associated with them. Operations performed on the associated operations performed on the job object affect all processes associated with the job object. Yeah, I mean, this is like extra functionality that we don't really care much about. So yeah, this is a whole bunch of information that we should take care on the next episodes. But for now, I think we can uh, stop the search on threads and processes and focus back on the virtual allocator. But for now, it's just the thing that we need right now. Sorry, the it can be the virtual allocator or rather the mmapper or even a copy file. I don't know. It depends on the size of the memory and how well do we want to do that. Or yeah, here's where we left off on the thing that we were doing. So yeah, I think this is the next thing for us to implement. I think I would like to yeah we have like these kind of dots that we have found across the several information that Windows lets us to understand. And for now, I mean all of that in the future will be our work will be to connect all of those dots and to start make sense of how can we implement some kind of a how can we use and implement this inside the debugger. So yeah, and yeah, I mean, so for coming back and for conclusion, we would say that yeah, since for example, if we would like to know how big this stack size, we'll need to get a thread context which has that data and make the virtual query and use the stack pointer from the context to gather up and see the sizing bytes of the stack for each thread. Yeah. Which is basically this. Where is the context? Well, yeah. So when you call the allocation base just means the pointer or the address where the virtual alloc that the virtual alloc return. The base allocation is determined at a time. A region of memory is not static. Once a single page in a region of reserved addresses becomes committed, the region is broken into one or more reserved regions and one committed region. Oh, cool. Okay. So, in that sense, what you have is, imagine that you have, let me draw it. So it will be something like this. Imagine that you have, oh, the same thing. We have our process with the bounds. And if we have all these things as free, or imagine that, or well, let's see, we have this memory, this address space as reserved, you know, and imagine that we in a certain part of the code we say, you know what, give me this portion and commit it. So now this is committed. Well, this is committed and all this is free. So now with this, if we call for the virtual query, we'll have this now two blocks of reserve, you know, they will return this way. And once I it's basically, yeah, like our it works as an allocator basically. Whenever you broke the whole region, then the system resolves for the size of these regions back, and that says, oh, you know, now we have this block which is this length and this block which is this length. And well, let me there you go. And the base address for each one, you know, which is what it does all the time. Similarly, when one of several page rewrite committed pages is changed to page read-only protection, the region is broken into multiple smaller regions. Oh, so yeah, I mean it discriminates along the state of the pages and the access, the type of the access modifier type that it has also. So you have like this kind of pool of, or yeah, this whole stack of different regions, everyone to be with either with, can be different different states or different uh, how do you say, how do you call this, um, reservation states, or the access privileges. Yeah. All right, so I think that's all. Just for conclusion, within each region are one or more pages of addresses. Uh, oh yeah, well, it just says that it can have protection. Yeah. So yeah. All right. So that sets are good for today. And yeah, I think now we have a better understanding of what does the Microsoft NT Virtual Memory Manager does whenever we run a process. And I implemented this. Let me just see if this compiles. I will assume that it they don't, but I can just do some stuffing here. Probably we have set us good for today, so that probably we found a good way to implement the loop-like code editing, which we just need a way to back up all the data that we have. So for the debug memory, for example, which it's more from a file point of view, but either way, it was good for us to understand more about the virtual memory system and how can we take advantage of it, you know. this has to be pointers. All right. So if I run this, it should be fine. Let me try to compile. There you go. We have the live code editing back. Everything looks fine, and yeah. All right. So now I would like to answer some questions, and yeah, I mean before going, I would like to just clear something about yeah. Don't worry if I mean sometimes yeah, if you see, if you watch me not probably implementing some functionality someday, or oh Jesus Christ, that was too loud. Yeah, I was saying that yeah, probably I mean if you, sometimes there will be the cases, or many of the times probably along this project, that we will not probably implement too much things, at this time, and probably we spend much of the time uh, searching for uh, uh, different the mechanics and the system, how everything works. I mean, probably as you have seen me do the research on probably most of the stuff right now. I mean, it has not been a lot of code action, I guess, but that's the way it is sometimes, and it's important to really dig deep into how does all these things work, so we can take advantage of it. I mean, this is an experimental debugger. It's not how fast you go coding and doing stuff. If you would like to do that, yeah, you can go and grab uh, some tool, so Java or something that helps you with that, I guess. But yeah, I mean, this is low level stuff doing, and I think that's the way it goes. You know. So yeah, I just wanted to clear that so people don't get upset about uh, uh, the all this. But yeah, all right. So yeah, I think I would like to answer some questions. If somebody have some of them, please. I'll be happy to answer them. All right. So I guess there's no questions. So I guess the stream has ended. Okay, so thank you very much for coming up in this stream. If you would like to post any questions, you can post them rather on YouTube or on the stream in Twitch, and I'll be happy to answer them. So yeah, I guess that's all for today, and I'll see you back on the next stream.